Yeah. So any questions before we start?
Okay, I have two questions.
Good.
Sometimes in those exercises, those problem homework, sometimes we find problems like are similar, like when you say proof some the specific statements, but it's are very close with the one that you already explained in class. Is like for example, like when we are proving the inverse, you explained and then you prove it in class, but it's almost the same procedure, you know, in the homework. Well, can we follow that, or you want us to use different letters or something, or
It's up to you. It makes no difference.
may not have for you? Okay.
Yeah.
Friday is will be closed according to Lemma calendar.
Okay. Oh, all right.
That would be 11.
Right. All right. So
will,
then I will not have an office hour that day. I'll change it to a different day. Is that what you're asking about?
yes.
Yeah. Okay. Thank you for telling me.
You're welcome.
I felt like it was the same person I thought I heard now. But you understand, like, it's not always from single to married. It was supposed to be married to single or married to married.
Okay, so let me start to record. Oh, no, we are recording. Excellent. So we're talking about vector spaces. And the most important example is Rn or Cn. And if we, so I don't have to write down everything twice, that F be either the real numbers or the complex numbers. So Fn is the set of all n tuples where the elements x1 up to xn, the coordinates of the vector, are elements of F. And we define vector addition in Fn coordinate-wise. x1, x2 up to xn plus y1, y2 up to yn. If we add two n tuples, we have to get another n tuple. You add the first coordinates, the second coordinates, and so forth, up to the nth coordinate. That's the definition of vector addition. And we define scalar multiplication. Scalar just means a number. So if lambda is a number in the field F, lambda times the vector is the vector you get by multiplying all n coordinates by lambda. So in this example, this is just one example of a vector space, Fn. You have addition of vectors defined coordinate-wise and scalar multiplication defined coordinate-wise. Right? So any statement about vector spaces in general has to be true for these vector spaces in particular. And in general, you have to know what is a vector space. Rn, Cn, Fn are examples of vector spaces, but there are many other vector spaces. And the definition, which you have to know, because you have the book in front of you, so it's easy to know it, but you should actually memorize this so it's sort of stuck in your head. A vector space V over the field F is a non-empty set with operations of vector addition and scalar multiplication that satisfy all of the properties that I'm not going to write down again. They're on page 12. Addition of vectors is commutative, associative. There's a zero vector. Every vector has an additive inverse. The number 1 is a multiplicative identity for scalar multiplication. There is there are distributive laws and so forth. So those are what something has to satisfy to be a vector space. And we also talked about subspaces. A subspace of a vector space V is a subset called W of V that is also a vector space with the same definitions of addition and scalar multiplication from V. So it contains the zero vector and so forth. And we looked at several examples of subspaces. And we saw how, for example, if you have two subspaces, the intersection is a subspace. The sum of two subspaces is a subspace. And we defined even direct sum, I think. Okay. All right. Any questions about this? This was everything we did in chapter 1. And now we're starting chapter 2. And the very first part of chapter 2 is completely fundamental to linear algebra. It's a notion of linear dependence and linear independence. And you want to be able to say something about what the dimension of a vector space is. And the idea is as follows. Suppose you have the line R, just the real line. So this is a vector space. So every vector in this space is just a real number. And you can think of the line as, in some sense, one-dimensional. Right? I'll call this R1. So this is just like Rn or Fn. This is just one coordinate. Right? It's one-dimensional. R2, this is a set of all pairs of real numbers. And in high school and pre-calculus, you learn to picture this as the XY plane or the X1, X2 plane. This is R2. And you think of this as two-dimensional. Or we could take R3. Instead of X1, X2, X3, let me just write this as X, Y, Z. So this is another vector space. And we think of this as three-dimensional. Okay. But this is all very vague. We haven't defined dimension. So our goal in this chapter, it'll take a bit of time, is to define dimension of a arbitrary vector space rigorously. Rigorously, what is the dimension of a vector space? So that's sort of our goal. And we're going to spend the next 2 weeks really working on this. So the beginning is to talk about linear independence and the span. So, okay, so here there are fundamental definitions. And the first is, what does it mean to talk about a linear combination of vectors? Well, suppose we have a vector space V over the field F. Suppose V1, V2 up to V sub M, this is some sequence of vectors in V. And that A1, A2 up to A sub M be scalars. So you can multiply a vector by a scalar. So I can take the vector V1 and multiply it by the scalar A1. I can take the vector V2 and multiply it by the scalar V2, and so forth. I can do this all along this line, all the way up to the vector Vm and multiply it by the scalar Am. And then I can add these vectors together. And this is what is called a linear combination of the vectors V1 up to V sub M. Okay. So let me look at some examples of this operation. Suppose I take the vector, this is in, let's say, R3. Or I can make it called the C3, it's all the same thing, in C3. Suppose I take the vector 2, 1, minus 3, and the vector 1, minus 2, 4. Let's say I multiply this vector by 6. I multiply this vector by 5, and I add. So what is 6 times this vector? You multiply every coordinate by 6. You get 12
plus 5.
6.
Sorry.
What?
Sorry, my bad.
12, 6 minus 18. Multiply this vector by 5. You get 5 minus 10, 20. You add, you get 17 minus 4, 2. So this vector is a linear combination of these two vectors. Right? So let me just say 17 minus 4, 2 is a linear combination of 2, 1 minus 3 and 1 minus 2, 4.
Professor,
Yeah,
so how do you determine which one is going to be vector, which one is going to be scalar?
a vector is a vector and a scalar is a number. You don't determine it. You can't say this is a vector and this is a scalar. This is not a scalar. You have to know what your vector space is. I said this is my vector space. So a vector has to have 3 dimensions, 3 coordinates. 6 is just a scalar.
Okay.
Can't be the other way around.
Vector is the number. All right.
Now,
Scalar
you
is
might
the
say, well, maybe everything is a linear combination of these 2 vectors. So let's make the following statement and then we can try to prove it. if instead of looking at the vector 17 minus 4, 2, I look at the vector 17 minus 4, 5, I claim this is not a linear combination of 2, 1 minus 3 and 1 minus 2, 4, right? So I claim this is not a linear combination. And how can we prove that? Well, it is certainly the case that in linear algebra, you're expected to know high school algebra. And in high school algebra, you learn about solving systems of linear equations. So the proof of this will be by contradiction. Suppose 17 minus 4, 5 is a linear combination of these two vectors. So suppose 17 minus 4, let me write it down here. 17 minus 4, 5 is some linear combination, let's say A1 times 2, 1 minus 3 plus A2 times 1 minus 2, 4. Right? Let's see, A1 times this vector is 2A1, A1 minus 3A1, and A2 times this vector is A2 minus 2A2, 4A2. And when I add these up, I get 2A1 plus A2, A1 minus 2A2, and minus 3A1 plus 4A2. So the logic here, the reasoning is very important. Here I have two vectors, 2, 1 minus 3 and 1 minus 2, 4. And I want to show that the vector 17 minus 4, 5 is not a linear combination of them. So we'll do it by contradiction. I'm going to suppose this is a linear combination of these two vectors and deduce from that a contradiction. So suppose 17 minus 4, 5 is A1 times the first vector and A2 times the second vector, right? So 17 minus 4, 5 equals this. Now, vectors are equal when they have the same coordinates. So this has to equal 17. This has to equal minus 4. And this has to equal 5. Right? For these two vectors to be equal. And this comes down to solving some linear equations, right? Because this says A1 and A2 have to satisfy the conditions 2A1 plus A2 equals 17. A1 minus 2A2 equals minus 4. And minus 3A1 plus 4A2 equals 5. Right? So A1 and A2 have to be a solution of these three equations and two unknowns. Let's just look at the first of them. I have 2A1 plus A2 equals 17, and A1 minus 2A2 equals minus 4. So spend a minute, this is just high school algebra, solve these two equations in these two variables, A1 and A2. So spend a minute and do that, and someone then just tell me the answer. Good. So A1 is 6, A2 is 5, but then we have to look at the third equation. Minus 3A1 plus 4A2 is minus 3 times 6 plus 4 times 5. That's minus 18 plus 20. That's 2. It's not 5. So if A1 and A2 satisfy these 3 equations, they satisfy the first 2. These have to be the solutions, but it doesn't satisfy the third. So that proves that 17 minus 4, 5 is not a combination of these 2 vectors. So some vectors are linear combinations of 2 others, and some are not, right? That's just what happens. Now, what's very interesting in linear algebra is if you take a set of vectors, so let V1, V2 up to V sub m be vectors in a vector space V, what is called the span of these vectors is the set of all linear combinations of them. So we write this as the span of V1 up to Vm. This is the set of all linear combinations of V1 up to V sub m. So the span of V1 up to Vm, this is the set of all vectors of the form A1 V1 plus A2 V2 up to A sub m V sub m, where A1, A2 up to A sub m are all possible choices of elements in the field. Okay? That's the span of a set of vectors. And a simple but important theorem about the span of a set of vectors is the following. So this is 2.7. I'll call it theorem 2.7. The span of a list of vectors in V is in fact the smallest subspace of V that contains all of the vectors. Contains all the vectors in the list. Okay, so that's a statement that needs a proof. So the first thing I will prove is the span, suppose the vectors are V1 up to Vm, is a subspace of V. So the span is all linear combinations. So for example, if I take the linear combination 0 times V1 plus 0 times V2 up to 0 times V sub m, 0 is a scalar times a vector. That's always the 0 vector. That's the 0 vector. I'll just write it like that to emphasize that, is in the span. So the span does contain the 0 vector. I need to show that the span is closed under vector addition. So suppose I have A1 V1 plus A2 V2 up to AN VN in the span, and B1 V1 plus B2 V2 plus B sub m these should be m's, v sub m in the span. So a1 up to am, these are scalars, and b1 up to b sub m, these are scalars. Then, let's see, suppose I just call this, no, I don't have to call it anything. If I add them, well, I'll call this u and w. Then the sum, u plus w, if I add this and this, I get a1 plus b1 v1, a2 plus b2 v2, up to a sub m plus b sub m, v sub m. This is again a linear combination of the vectors in the list. And if I take a scalar c and multiply it, for example, by the vector u in the span, that's c times a1 v1 up to am vm. That's ca1 v1 up to cam v sub m is in the span. So the span of a list of vectors is a set of vectors that contains the zero vector and is closed under vector addition and scalar multiplication. So what I just showed is the span of v1 up to vm is a subspace of V. Moreover, if I take the vector v1, I can write that as 1 times v1 plus 0 times v2 plus 0 times v3 and so forth, up to 0 times vm. So each of the vector v1 is a linear combination of v1 up to vm. So this is in the span. And in fact, for all I from 1 up to m, the vector v sub I, you can write that as 0 times v1, 0 times v2, 0 times v sub I minus 1, 1 times v sub I, 0 times vi plus 1, up to 0 times vm. So this is in the span. So the set of vectors v1, v2 up to v sub m is contained in the span of v1 up to v sub m. So if I have a set of vectors or a list of vectors, their span is a subspace and it contains the vectors v1 up to vm. But what I want to show next, what I need to show is that this is the smallest vector subspace with this property. So suppose I take any subspace. So if W is a subspace of V that contains V1 up to Vm, then because W is closed under vector addition and scalar multiplication, W contains every linear combination of V1 up to Vm. So the span of V1 up to Vm is contained in W. So this means that this is the smallest subspace of the vector space that contains the vectors V1 up to Vm. because this is a subspace and it's contained in every subspace that contains V1 up to Vm. And we say, yeah,
So
question?
W means subspace, right?
So if W is any subspace of V that contains V1 up to Vm.
Okay.
So we say that the set of vectors V1 up to V sub m spans the vector space V if the span of all these vectors is equal to the whole space.
Okay.
So again, there's the most important example. Let me just look at the following. Suppose I let the vector space be R2 and take the vector V1 equal to 1, 0 and V2 equals 0, 1. So if I look at the span of V1, V2, that's the set of all linear combinations A1, V1 plus A2, V2 for all A1 and A2 in R. So this is A1 times the vector 1, 0 plus A2 times the vector 0, 1. This is the set of vectors A1, A2 for all A1, A2 in R. And this is exactly the definition of R2. Okay. So these two vectors span R2. And there can be other sets of vectors that span R2. You could have 10 vectors and the span of those 10 vectors is R2. But in any case, these two vectors span R2. And now we come to a very important definition. A vector space V is called finite dimensional. If some finite list of vectors spans V. Okay. So not every vector space is spanned by a finite list of vectors, but any one that is called finite dimensional. Here's another example of a vector space. You know what a polynomial is. A polynomial with coefficients in the field F. Let's use Z for my variable. Like this is a polynomial, A0 plus A1Z plus A2Z squared. Some finite list of these terms, powers of Z that stop at some point. where these coefficients of the polynomial are elements of the field. And that P, script P of Z be the set of all polynomials with coefficients in F. And this is a vector space. This is another very important example of a vector space. So if we have two polynomials here, let me just write down some very simple examples. Suppose P of Z is 7 plus 6Z plus 19Z cubed. And Q of Z is 1 minus 5Z minus 2Z squared plus Z to the 17th power. So I can add them, right? Just add polynomials. P of Z plus Q of Z is 8 plus Z minus 2Z squared plus 19Z cubed plus Z to the 17th, right? And I can take a polynomial and multiply it by a scalar. So 3 times P of Z, that's 3 times 7 plus 6Z plus 19Z cubed. That's 21 plus 18Z plus 57 Z cubed. Right? So I can add polynomials. I can multiply polynomials by a scalar. I can check that all of the conditions that are required to have a vector space are satisfied. So P of Z is a vector space. It's a vector space, and the elements of this are just called polynomials, the vector space of polynomials. Any question about this? I mean, polynomials are things you know well. And the polynomial A0 plus A1Z, A2Z squared up to A sub M Z to the M, we say this has degree M if the coefficient A sub M isn't 0. Right? So for example, P of Z equals 2 plus 3Z plus 5Z squared has degree 2. P of Z equal 2 plus 3Z plus 5Z squared plus 0 times Z cubed also has degree 2. It doesn't have degree 3 because this coefficient is 0. The degree is the highest power of Z that appears in the polynomial with a non-zero coefficient. So that's the degree. And we can look at all polynomials, but we can also look at P sub M of Z, which is the set of all polynomials of degree at most M. Now, okay, let's just see. If you take the polynomial Z, the degree of Z is 1, because this is Z to the first power. If you take the degree of the constant polynomial 7, that's 0, because P of Z, this is like 7, which is 7 times Z to the 0. The highest power of Z with a non-zero coefficient is the 0th power. So the degree of the number 7 is 0. But what about the constant polynomial 0? That doesn't fit into this because there's no coefficient in the polynomial that's non-zero. we say the degree of 0 is minus infinity. So some people don't like minus infinity. They say it's undefined, but either one will work equally well for us. So for example, P1 of z, which is all polynomials of degree at most 1, is everything of the form A0 plus A1z, A0, A1, elements of the field. All linear polynomials are constant polynomials. In P of 2 of z, we can have polynomials of degree up to 2, A0 plus A1z plus A2z squared, and so forth. And again, P sub m of z, this is all polynomials of degree at most m. And this is in fact the span of a finite set of polynomials. If I take the polynomials 1z, z squared, z cubed, all the powers of z up to z to the m, the set of all linear combinations of these is the set of all polynomials. So if I look at, for any m, all polynomials of degree at most m, this is a finite dimensional vector space because it's spanned by a finite set of vectors. So P sub m of z is finite dimensional for all m. All right. Any questions about this? So I define finite dimensional. You might ask, when do we say that a vector space is infinite dimensional? So it has an easy definition. A vector space V is infinite dimensional if it is not finite dimensional. And the most obvious example now of an infinite dimensional space is the space of all polynomials. So I might even state this as a theorem. P of z, this is all polynomials of any dimension, is infinite dimensional. And the proof can be given as follows. Let P1 of z up to P sub m of z be any finite list of polynomials. So suppose we let the degree of P sub I of z equal d sub I for all of these m polynomials. So every polynomial has a degree, and let d sub I be the degree. And this is a finite set of integers. So that d be the maximum of the degrees of my polynomials. So if P of Z is in the span of these polynomials, then P of Z is some A1 times P of Z, P1 of Z up to AM P sub M of Z. It's some linear combination of these polynomials. And when you multiply a polynomial by a scalar, you don't increase the degree. And so this has degree at most, the degree of the maximum of any of the degrees of these polynomials, at most D, this maximum. So Z to the D plus 1, this is a polynomial of degree D plus 1. This is not in the span. So for any list of polynomials, there's some polynomial not in the span. So the vector space of all polynomials cannot be the span of a finite set of polynomials. So it is not finite dimensional. That's the upshot of this discussion. Now, I'm about to prove some abstract statements about vector spaces. And I'm going to go over it today. I'll go over it again on Wednesday. I'll go over it again probably next Monday, because it's the basis of all of the linear algebra we're going to do. And it takes some degree of time to understand the concepts. So a list of vectors, V1 up to V sub M, is called linearly independent. If the only choice of scalars, A1 up to A sub M in the field, such that the linear combination A1 V1 A2 V2 plus ... plus A sub M V sub M equals the zero vector, the only way this can happen is if you choose all the scalars to be zero.
Professor,
Yeah,
so you mean V1 A1 has to be equal to 0?
no, the vectors are not equal to zero. You say that the set of vectors or this list of vectors is linearly independent
Yes.
if the only linear combination of them equal to the zero vector occurs when all the scalars, the A's are scalars, not vectors.
Okay.
All right.
Thank you.
So here's an example. Suppose I take V1 to be 1, 0 in R2 and V2 to be 0, 1 in R2. So my vector space is R2. If A1 V1 plus A2 V2 is equal to the zero vector, what does that mean? It means A1 times the vector 1, 0 plus A2 times the vector 0, 1 equals the zero vector 0, 0. But what is this? This is A1 times 1, 0 is the vector A1 comma 0. And A2 times the vector 0, 1 is 0, A2. So A1 times 1, 0 plus A2 times 0, 1. That's A1, 0 plus 0, A2. That's A1, A2. The only way that equals the 0 vector, if and only if A1 equals A2 is 0. So these two vectors this one and this one, they're not the 0 vector, but they're linearly independent, because the only time a linear combination of them could give you 0 is when all the scalars are 0. The A1 and the A2 both equal 0. Right? And we know lots of examples when we look for them of linearly independent sets of vectors. For example, you could take 1, 0, 0, 0, 0, 1, 0, 0, and 0, 0, 1, 0 in R4. Because the only linear combination, if you take any linear combination of these, what you get is A1, A2, A3, 0. And the only way this equals the 0 vector is if all these scalars are 0. So these are three linearly independent vectors in F4, in R4. Or in the vector space of polynomials, P of Z, the polynomials or the vectors 1z, z squared, z cubed are linearly independent. Of course, if you take a linear combination of them, A0 plus A1z plus A2z squared plus A3z cubed, that's the 0 polynomial if and only if all the coefficients are 0. Right? So this concept of linear independence, this takes some time to become familiar with. And because if you define linear independence, we should define linear dependence. So a list of vectors V1 up to Vm is linearly dependent if they're not linearly independent. Yeah, let's look at some examples. I claim that the vectors 2, 3, and 1 minus 7 are linearly independent. Proof. Suppose A1 times 2, 3 plus A2 times 1 minus 7 is the 0 vector. This is 2A1, 3A1 plus A2 minus 7A2 equal to the 0 vector, or 2A1 plus A2, 3A1 minus 7A2. That's supposed to be the 0 vector. Each coordinate has to be 0. So 2A1 plus A2 equals 0. 3A1 minus 7A2 equals 0. If you solve these two equations and two unknowns, you get that the only solution is A1 equals A2 equals 0. So this means that we prove what we wanted to prove. These two vectors are linearly independent. Suppose I take the vectors 5 minus 4 and minus 10, 8. Are these independent, linearly independent or not? So again, I look at, suppose A1, V1 plus A2, V2 is the 0 vector. Let's see, what is that? A1, V1 is A1 times 5 minus 4. That's 5A1 minus 4A1. And A2, V2 is A2 times minus 10, 8. That's minus 10A2, 8A2. So A1, V1 plus A2, V2 is equal to 5A1 minus 10A2 minus 4A1 plus 8A2. And we want to know, when is that equal to the 0 vector? So then 5A1 minus 10A2 has to be 0, and minus 4A1 plus 8A2 has to be 0. So we have to solve these two equations and two unknowns. From the first equation, we get 5A1 equals 10A2, or A1 equals 2A2. From the second equation, we get 4A1 equals 8A2, or A1 equals 2A2. So for any value of A2, if you let A1 equal twice that, we get a solution. So for example, if you let A1 equal 2 and A2 equal 1, 2 times 5 minus 4 plus 1 times minus 10, 8. If you check, that's the 0 vector, which means some linear combination of these two vectors is 0, and the scalars are not both 0. So these two vectors are linearly dependent. Yeah. So as you see, among other things, there's a lot of there are many linear equations in linear algebra. Let's see, here are problems to do. Right now, prove that the vectors 1, 2, 3 and 2, 3, 4 are linearly independent. Right? So how do you prove that? You have to say, suppose A1 times 1, 2, 3 plus A2 times 2, 3, 4 is the 0 vector.
Mhm.
Show the only way this can happen is if A1 equals A2 equals 0. So spend a minute trying to prove that. Let's see. What will we say? A1 times 1, 2, 3 plus A2 times 2, 3, 4. This is the vector A1, 2A1, 3A1 plus 2A2, 3A2, 4A2. This is equal to A1 plus 2A2 2a1 plus 3a2, 3a1 plus 4a2. And we want to know for what values of a1 and a2 does this give the zero vector. So each of these coordinates has to be 0. a1 plus 2a1 is 0. 2a1 plus 3, sorry, a1 plus 2a2 is 0. 2a1 plus 3a2 is 0. Let's see. If I multiply the first equation by 2, I get 2a1 plus 4a2 equals 0. The second equation was 2a1 plus 3a2 equals 0. If I subtract, I get a2 is 0. If a2 is 0, then a1 is 0. So even just looking at the first two coordinates, the only way they're both equal to 0 is if a1 and a2 are 0. So that means that these vectors are linearly independent. All right. Questions about this? Okay, so I'm now going to prove a very important.
Excuse me, Professor.
Yeah,
You say you multiply the first one by 2, right?
well, I'm not sure what you mean here. I mean down here. Yeah, I multiplied this equation by, I'm just solving two equations. If I multiply this by 2, I get 2a1 plus 4a2.
But what about minus 2?
Where's minus 2? There's no minus 2 anywhere.
Because you want to cancel one, right?
I took this first equation and I multiplied it by 2 to get this equation. I took the second equation and I didn't do anything to it. And then, so I have these two equations. When I subtract, I get
Yes,
a2 is
but when
0.
I got it. Okay.
Okay. Okay. So what I'm about to do is very important. This is on page 34. It's Lemma 2.21. And it says the following. Suppose V1 up to V sub m is a linearly dependent list in the vector space V. There exists a J in 1 up to m such that the following two statements hold. The vector Vj is actually in the span of the vectors V1, V2 up to V sub j minus 1. And second, if the jth vector V sub j is removed from the list of V1 up to Vm, the span of the remaining vectors doesn't change. So the span of V1 up to V sub m is equal to the span of V1 up to V sub m with V sub j removed. Right? So if you have this depends on the vectors being linearly dependent, right? So if the vectors are linearly dependent, so this is the proof of the proof of the first statement. Linear dependence means there's some linear combination, A1 V1 plus A2 V2 up to A sub m V sub m equal to 0, with the coefficients A sub I not all 0. So choose the largest coefficient A sub j not equal to 0. So then what you have is A1 V1 A2 V2 up to A sub j minus 1 V sub j minus 1 plus AJ VJ is equal to 0, because all the higher coefficients are 0. So if I take this equation, I can write this as, AJ VJ or minus AJ VJ is A1 V1 A2 V2 up to A sub j minus 1 V sub j minus 1. And because AJ is different from 0, I can divide by it. So I get V sub j is minus A1 over AJ V1 minus A2 over VJ over A2 over AJ V2 up to minus A sub j minus 1 over A sub j V sub j minus 1. So Vj is a linear combination of the first j minus 1 vectors. So Vj is in the span of V1 up to V sub j minus 1. So that proves the first statement. And to prove the second, if V is in the span of V1 up to Vm, then V is some linear combination A1 V1, say AJ Vj up to A sub m V sub m. But V sub j can be written like this. So V is A1 V1 up to A sub j minus 1. Actually, I should use different letters here. If V is in the span, I'll use letter C, C1 up to C sub m. So, and just to be consistent maybe with the notes of the book, this is the vector U. So if U is in the span of V1 up to Vm, then U is some linear combination of V1 up to Vm. So U is C1 V1, C sub j minus 1, V sub j minus 1, C sub j, V sub j. But I can write V sub j like this. V sub j is minus A1 over AJ V1 up to minus A sub j minus 1 over A sub j V sub m plus CJ plus 1 VJ plus 1 up to CM VM. And this is a linear combination of all the vectors in the list except VJ. So this is in the span of the vectors v1 up to vm with v sub j removed out. Right, so this is all written down very legibly in the book, but I'm really just explaining what it means. This is the idea. So if you have a linearly dependent set of vectors, you can take away one, and the span of the smaller set is the same. It's no smaller than the span of the original set. So I have a little bit of time, and I'm going to prove one last result. All these things are really very difficult to understand when you're beginning to study all this. So take some work at home, definitely. So this is on page 35, 2.23. It says that the length, the number of any linearly independent list of vectors in a vector space is less than or equal to the length of any spanning list. So how does the proof of this statement go? Let me also make it very explicit what this means. So the length of a linearly independent list. So let U1, U2 up to U sub m be linearly independent. So these are vectors in the vector space that are linearly independent. And let W1, W2 up to Wn be a spanning set. That means the whole vector space is the span of W1 up to Wn. And we want to prove that m is less than or equal to n.
Professor, you said proof m less than equal to n or greater than.
So we want to prove, this is the goal.
Okay.
We want to prove that m is less than or equal to n. All right. Now, this is a spanning set. So every vector is a linear combination of these vectors. So this implies that if I take the n plus 1 vectors, U1, W1, W2 up to Wn. So I added the vector U1 up to Wn. This is linearly dependent because U1's a linear combination of these. Right? This is linearly dependent. And so by the lemma I just proved, I can remove one. See, what the vector I just proved was, if I have a linear combination equal to of these vectors, that allows me to throw away one of the w's and still have a spanning set. I can remove one of the w sub j so that the set U1, W1, let me put a hat over this to mean we leave this guy out, up to Wn still spans the vector space. Now, if I take the vector u2 and add it to this list, u2, u1, w1, I've thrown out wj up to wn, this is dependent because u2 is a linear combination of these, and it can't just depend on u1 because u2 and u1 are linearly independent. So there's some w involved in that, and I can throw out another w. So I end up with a list of vectors u1, u2, w1. I throw out some vector wj1. I throw out some vector wj2 up to wn. I can throw out one of these vectors, and now I still have n vectors which span the vector space, and they include u1 and u2. And
Professor,
yes,
yeah, I can see.
sorry. But the idea is, as I add one by one the vectors u1, u2, u3, and so forth to the list, I end up with a set of n vectors which include the u's plus some of the w's that spans the space. And I can't run out of w's because if I did, the u's would be linearly dependent, and they're not. All right, so I don't think what I just said is enough to understand this theorem. So, and it takes more time than we have. So I'm going to start the class on Wednesday by going through this section completely and more slowly. But the important thing is to study section 2a a lot, and especially pages 34 and 35. And this is really fundamental linear algebra. And even though I think the syllabus said I'm going to go on to section 2b on Wednesday, I'm going to spend a lot of time going through this section again because it really is central to what we do. Okay. Any questions about anything? All right, so that's all for today. I do have an office hour at 1:30, and I'll change the office hour on Friday to make it sometime either Wednesday or Thursday. Okay.
Professor,
Yes, sir.
those office hours, just
Oops.
at that time, that one, for example, today, 1:30, I just go in to
Yeah.
the Zoom.
Yeah, it's for all my classes. It's just like, you know, when you meet on campus and you have an office hour, that means I'm in my office and anyone from any of my classes can come by to ask questions. So it's not just for linear algebra, it's for other classes as well, but you know, everyone gets a chance to ask whatever they want to ask.
So you said today 1:30, right?
Yes.
Okay, thank you.
Thank you.
Okay. All right. Bye all.
Bye.
Yeah.